Welcome to the new chapter of ionic polymerization. We have discussed about the radical polymerization and others. Now, if you recall that previously we discussed about the comparison between ionic and radical polymerization. We had a discussion about the living polymers and dormant polymers. We asked about the polymerizability of the polymer process or monomers under the head of thermodynamic discussion. Now, in this particular chapter, we will discuss about the classification of various ionic species. We will discuss about the effect of solvents, because solvent play a vital role in the polymerization process, especially in ionic polymerization. Then we will discuss about the ionophores and ionogens, ionic pairs. Then we will discuss about the covalent species, which are again integral part of this ionic polymerization. We will have discussion about the equilibria between the free ions and ionic pairs under the edges of conductance studies. We will have a look of the heat and entropy dissociation of ionic pairs. Since we are discussing about the ionic pairs, we will have a look about the different types of ion. Then as a core part of ionic polymerization, we will discuss about the initiation and propagation step in ionic polymerization. We will have a discussion about the effect of solvating agents. So, let us start with the classification of various ionic species. Now, usually the matter in bulk is electrically neutral, and each time it incorporates electrically charged species, that is ions or their aggregates. Sometimes their opposite charges have to stabilize each other exactly. So, conceptually the easiest procedure converting electrically neutral molecules into electrically charged ion, this outcome from electron ejection. This is referred as ionization, and this is usually triggered by means of either photolysis or radiolysis. Now, these two things are very much popular nowadays. Now, it is the basic protocol behind it is that it is usually triggered by the action of high energy projectiles, maybe gamma rays, maybe X-rays, maybe speedy electrons, etc. So, these things look into. So, the prerequisite is that you must have those high energy projectiles, or you may have these high energy particles to carry out these processes. Now, the ejected electrons, they are usually captured subsequently with the aid of some neutral molecules, yielding then the negative ions, while ionized molecule constitute the positive ions. So, a direct ionization of a neutral molecule, it may require a massive amount of energy, and sometimes it is 9 electron volt per mole or even more. So, such quantities of energy are readily available in radiolysis and in photolysis, induced with the aid of radiation of very short wavelength, sometimes vacuum UV, but no longer in the photolysis induced by means of a near ultraviolet or visible light. Now, the latter enable the electron transfer, provided that some electron acceptors of sufficiently excessive electron affinity is reachable in the neighborhood of radiation absorbing electron donors. Now, let us have a brief look about the effect of solvent. So, various species may act as electron acceptor, even some solvent may play these roles. For example, if we are talking about the near UV irradiation of aromatic amines in water, they sometimes yield the respective radical cation and solvated electrons. So, water acts here as an electron acceptor. So, it all depends on the affinity and it all depends on the solvent, on the solvation ability of the reactant in question. So, in the media, however, in the media, poorly solvating ions such as hydrocarbons of same irradiation of amine, they sometimes produce neutral radicals and not the ions. Now, the nature of solvent is important, even it does not act as an electron acceptor. So, for example, like irradiation of trimethylamine and biphenyl. Now, beta is the acceptor. In the acrylonitrile solution, this yields an exciplex with the dissociation into the pairs of ion, and sometimes referred as Et3n plus and beta minus. Their solvation makes the process feasible. Sometimes, on the other hand, the toluene solution, there is no electron transfer take place and ions are not formed, and the absorbed excitation energy is dissipated through the fluorescence. So, although a monophotonic process resulting from irradiation by near ultraviolet or visible light does not provide enough energy for direct ionization. So, ions may be formed by the biphotonic process. Let us take the example that the ionization potential of benzene being 9.2 electron volt per mole is too high to allow the formation of its radical cation by a monophotonic UV irradiation. So, this particular thing need to be addressed, or this particular thing need to be keep in mind while selecting the solvent, a proper solvent. Now, this however, the excitation energy of a benzene to the singlet, like say 4.84 electron volt per mole, this is followed by the intersystem crossing to the triplet, and they are having the energy domain of 3.7 electron volt per mole. This may lead to ionization caused by the consecutive absorption of 2 photons. So, the first yielding the triplet while the second causing its ionization. So, this is the sequential effect, that how you can optimize the things based on the low energy concept. Now, encounter of a species of a very low ionization potential with another of a very high electron affinity might lead to electron transfer and the formation of oppositely charged ion, even in the absence of radiation, sometimes provided that the reaction takes place in a well solvating media. So, indeed, the solvation of resulting ions contributes substantially to driving force of the process. So, the reaction of alkali metal with the aromatic hydrocarbons, it provides another example stressing the role of solvents in electron transfer process. So, in well solvating media, this reaction yields aromatic radical anions and alkali cations. So, you may have enough opportunity or enough options to carry out these reactions. Alternatively, ions are formed on transfer of some charged moiety from one neutral molecule to another one, and proton transfer from a covalent acid to a covalent base is the most common example of such a process. Therefore, the anhydrous perchloric acid, sometimes it reacts with the equimolar amount of water, yielding the crystalline ionic salt, sometimes referred as H3O plus ClO4 minus. In the non-conducting solution of hydrogen bromide in sulfur dioxide, this may become the conducting on addition of an equimolar amount of water, that may be attributed to the formation of free H3O ions or bromide ions. Now, let us take about the ionophores and ionogens or ionic pairs or a covalent species. So, these ionophores in the polymerization system, they can be called as the charge carriers or charge bearers. Now, it is also known as ion complexers, which was first used as anti-cochineal agents. So, many solids, they are built up of neutral molecules cemented together by the van der Waals forces, and these forces are very weak forces. So, when they are joined together by van der Waals forces, while other known as ionic crystals, they are composed of iron as their building blocks. So, these building blocks are later referred as the ionophores, dissociate the quantitatively into the free ions in media in which they are soluble. So, these ionophores are specific molecules that carry specific cations and facilitate their transport through biological membranes. So, while taking the application of all those things, we may consider this particular approach in our mind. So, they are the molecules that act as a membrane shuttles for the particular ion across the lipid membrane without the expenditure of energy. Now, let us have a look about the ionogens. Now, the ionic molecules that react with the solvent, they forms or they are forming then the oppositely charged ions, they are classified as ionogens. Let us take the example of one example, that is a dissociation of acetic acid in water. So, while we discussed about the basic methodology, basic protocol of these ionophores and ionogens, let us discuss about the generalized structure of those ionophores. Now, these ionophores contain hydrophilic centers that binds specific ions and a hydrophobic protein that interact with the lipid interior to the membrane. So, most ionophores they adopt a cyclic ring formation by concentrating oxygen nitrogen functional group at the center of their structure to associate with the cation. Now, with the hydrophobic group in contact with the say acyl group of the membrane, the ionophore is able to dissolve and diffuse to the opposite side of the membrane, so that they may become very selective in this nature. Now, ionophores, when we talk about the various spectrum of ionophores, ionogens, then the things arises related to the classification of ionophores. So, these can be classified either based on the mechanism of their action. Now, again they are subdivided as mobile carrier ionophores. Now, these bind to a particular ion and shield it charged from the hydrophobic environment of the membrane. Now, they form the lipid soluble complex with the cation, which then diffuse across the membrane. Sometimes by reversibility binding to the ion to form the lipid soluble complexes, which rapidly diffuses across the membrane. Now, they catalyze the passive transfer of cation across the otherwise impermeable hydrophobic membrane. So, the process is become more and more selective. Now, usually when we carry out this particular thing, this is a three-step process. One is that the complexation of ionophores with the ion. The second is the diffusion of the complex via the membrane interface to the other side of the membrane, and third one is the reverse complexation process. Now, another aspect is the channel forming ionophores. Now, these ionophores they introduce a hydrophilic pore into the membrane, allowing the specific cation to pass through without coming into contact with the hydrophobic initiator of the membrane. So, this is again a very beautiful approach, so that the polymeric chain may not get into the dead zone. Now, these are the channel forming ionophores that usually are having the larger molecules in nature. Now, another route of classification is based on the chemical structure. So, one is that the polyether ionophores, that is the mononencin or madoresin. Then peptide ionophores, they are the biological polymers. Then cyclodespeptide, that is the macrocyclic compound containing the tetrahydrofurane carboxylic acid residues linked together. Then cryptates, that is the synthetic bi and polycyclic multidentate ligands for a variety of cations. Then crown ethers. Now they create the electrochemical gradient resulting in changes in the physiological state of cell structure, like oxidative phosphorylation, sometimes osmotic balance, then neurotransmission, then cell signaling, then hormone, etc. Now let us talk about the ion pairs. Now some molecules which are basically not associated ions, when they present in a solution along with other molecule, they start acting as an ionic molecule. So let us take the example that adduct BF3OC2H5 is not an ionic pair. I am writing this one BF3OC2H5 2. This is not an ionic pair and it does not dissociate into BF3OC2H5 anions and minus and C2H5 plus cations, although it acts as if it were on the ionic pair. Now it transfer the positively charged C2H5 moiety to the vinyl ethers and thus initiate the cationic polymerization. Now in chemistry, the tight ion pair concept usually introduced by Salvinstein described that the interaction between a cation, anion and surrounding solvent molecules. Now in ordinary aqueous solution of inorganic salt, an ion is completely solvated and shielded from the counter ion. In less polar solvent, two ions can still be connected in some extent. Now let us have a look about those tight or intimate contact ion pair. Now there are no solvent molecules between their two ions. So when we talk about the solvation, so if the solvation increases, the ionic bonding decreases and a loose or a solvent shared ion pair results. The ion pair concept explains the stereochemistry in solvolysis and you see here we have this is the tight ion pair R plus X and then this is you see that the solvent separated ion pair and when this solvent acts its role, then it may become the free ions like R plus and X negatively charged. So an ion in a solution may approach its partner surrounded by a tightly attached solvation shell with no hindrance until it contacts the shell. So thereafter the resulting associate may retain its structure of loose solvent separated pair or it may collapse, squeezing out the solvent molecule or molecules by separating the ions. Now in latter case a tight contact pair is formed and the essence of this is that these two alternative outcome of the association are equivalent to the establishment of an equilibrium between the loose and the tight ion pairs. So the two type of ion pairs from thermodynamically distinct species each characterized by its own specific properties. Now let us have a look about this concept, that is equilibria between free ions and ion pairs. Now this is a very important thing while discussing about this ionic polymerization, that how we can establish the equilibria between the free ions and ion pairs. So we discussed about this free ion, we discussed about these ionic pairs. So the foremost thing which we need to address, that is called the conductance studies. Now in solutions of partially dissociated salt for conducting free ions, sometimes they are in equilibrium with the non-conducting ionic pairs. Now let us have a look about this one. This is A, B. They are the ionic pairs. Now, if we perform this the dissociation study, then it may become A minus plus B plus. Now, the dissociation constant this K dissociation is derived commonly from the dependence of the equivalent conductance of the studied solution, and sometimes refer as like this. Now, on the concentration of salt is usually denoted by C, that is the concentration of the salt. Now, this is in conjunction with the values of limiting conductance, and the limiting conductance is sometimes referred as this one. So, this may be referred as, or mathematically it can be represented like this. This is for C tends to 0. Now, this latter needed in the calculation of this K dissociation. The simplest procedure is attributed to the Ostwald. This lead to the values of both constant, that is this conductance, limiting conductance, and K dissociation. So, if we try to formulate the things, then it experimentally, then it may give you the linear plot, and we can calculate or we can represent this in this particular mathematical equation upon K dissociation. This one. Now, this thus this the limiting conductance is given by the reciprocal of the intercept, where the reciprocal of the slope provides the value of K dissociation, limiting factor square, from which the K dissociation may be computed. So, by this way we can calculate the K dissociation as well as the limiting conductance. So, by this way we can establish the equilibria between free ion and ionic pairs. Now, this relation is purely based on the mass law that is valid for sufficiently dilute solution. Since then the activity coefficient differ only negligibly from the unity. Now, for real solution these this particular thing deviates substantially from ideality, and it is necessary to modify this procedure, or which the mathematical procedure which we discussed a priori. Now, the best and most widely used modification that is applicable to such system was developed by Fuss. Now, in this particular protocol which was developed by Fuss, that is it calls the plotting of F versus the conductance, F upon conductance versus the concentration of conductance. Now, F is square F, where F and small f and capital F, they are the function of salt concentration C and the conductance. So, as well as the temperature, dielectric constant and viscosity of the investigated solution. So, usually a computer program is needed for the calculation of those functions capital F and F. Now, these computer programs are readily available, and the values of limiting conductance and K dissociation usually derived from the Ostwald plot and used to start the computation. So, usually when we talk about the values, the intercept of these first plot gives again 1 upon limiting conductance, and its slope yields the value of 1 upon k dissociation and square of limiting conductance. So, in the course of the studies of ionic polymerization, dissociation constant is usually kept low, and that is it is around 10 to the power minus 12 m. This need to be determined. Now, to get the reliable values for the slope and intercept of this plot, it is imperative to extend the measurement of to a very low concentration of the salt, sometimes often lower than 10 to the power minus 6 m. Otherwise, the slope is too low and the intercept too high. Now, let us see which this is the plot which we are talking about. Now, you see here the figure, the both error reinforce each other. So, the error in such a case computed the k dissociation, and this could be a very large. So, you can have a look of this plot. Now, let us have a discussion about the heat and entropy of dissociation of ionic pairs. Now, sometimes if we talk about the equation deduced in the preceding section which we discussed earlier, the k dissociation lead to the delta H of standard delta H of dissociation. This is equal to Na upon E square upon epsilon R1 plus R2 into 1 minus d ln epsilon upon d ln t. Now, since d ln epsilon over d ln t is usually smaller than minus 1, sometimes minus 1.16 for the tetrahydrofuran and minus 1.33 for diethyl ether and so on. So, the dissociation of bulky ion pair is expected to be slightly exothermic. So, the values of enthalpy under the initial start that may be calculated from this equation agree fairly well with the experimental ones for bulky ion in the poorly solvating media. Now, when we talk about the heat and entropy dissociation, that is for a small ion in a well solvating media, the exothermicity is substantially larger. Now, its increase arises from more extensive degree of solvation of free ions than of the associated ion pairs. Now, consequently, the dissociation of such pair decreases the entropy of the system. Sometimes it immobilizes the solvent molecule that becomes incorporated into the solvation shell of free ions. Now, let us have a look about this dissociation aspect. So, now tight and loose ion pair, which we discussed previously, that they are present in the system. Therefore, the equilibrium between the free and paired ions is given by the tight pairs, that is KTL, loose pair, that is K, that gives you the free ions. So, the observed K dissociation is given by K dissociation L upon KTL 1 plus KTL, where this K dissociation L, this denotes the equilibrium constant of dissociation of loose ion pairs, and this KTL, this is the equilibrium constant of conversion of tight into loose pairs. So, at high temperatures, when KTL is less than 1, then the slope of want of line is referred as delta H under the standard condition TL plus enthalpy of dissociation L upon R. Now, here this delta H TL is naught and delta H L, this denote the heat of conversion of tight into loose ion pairs and heat of dissociation of loose pairs respectively. So, by this way we can calculate this one. Now, on the other hand, at a very low temperature when KTL is greater than 1, the slope is lower, being equal to delta HL naught only. So, the curvature of the want of plot, this deals with the propagation of living polymers, which we discussed in the previous segment. Now, the equation for enthalpy of dissociation, this shown the beginning of this particular section. This applies to the enthalpy of a dissociation L, since the bulky well solvated ions are not further solvated on their dissociation. So, in this particular chapter we discussed about the ionogens, ionophores, etc., their equilibrium concepts. We discussed about the heat and entropy of various dissociation pairs. We discussed about the efficacy of those ion pairs in the polymerization process, and we will continue this particular approach in the next lecture. And you may look into the various references which we have enlisted in the in this particular slide. Thank you very much.